Deduplicating and flattening hierarchical records, like nested arrays in API outputs or JSON log files, is a routine ingestion task. This question tests recursive limits, stacks, and data type safety. In transaction databases and API payloads, nested array schemas represent hierarchical data structures. Deep nesting levels commonly exceed hundreds of sublists. A classic Python data engineering coding question is to flatten a multidimensional array. Let's see why basic recursion causes pipeline crashes at production scale. A common solution is to write a recursive function. The algorithm sweeps the array. If it encounters a scalar, it appends it to the output. If it finds a list, it recurses. The simple recursion works on small lists, but it hides a critical execution flaw. Python has a default call stack frame limit of 1,000. In enterprise schemas, such as complex Avro logs, nesting levels can easily exceed this limit. Every recursive step adds a stack frame. At nesting level 1001, Python throws a recursion error, terminating the ingestion pipeline immediately. Let's build a solution that avoids call stack limits. The optimal solution shifts call frames to a heap-allocated list stack. We push the input list onto our custom stack. While elements remain, we pop the top item. If the item is a list, we reverse its contents and push them back. If it's a scalar, we append it to our result list. This depth-first search approach processes arbitrary depth safely with a constant call stack frame count of 1. Let's check our edge cases. In Python, strings are iterable. If we use a generic iterable type check, a string event like click gets character split. We must check for lists specifically. Also, empty sublists are safely handled by the reverse extend loop as a no operation. Finally, we can rewrite this using yield statements to allow lazy, memory-efficient generator processing on streams. Remember the explicit stack DFS blueprint. When developing recursive parsers for tree schemas, nested JSON or partition files, avoid implicit recursion calls. Maintain your stack in a heap list, push, pop, checklists, and process. Master this pattern to write resilient, stack-safe ETL pipelines. Let's analyze the naive unbounded recursion trap approach. Time complexity, O of n. Space complexity, OD. Call frames right pointing arrow, recursion error. Recursion adds frames directly to the Python call stack, causing crashes when nesting depth D exceeds 1,000. Let's analyze the iterative stack DFS correct approach. Time complexity, O of n. Space complexity, OD, heap stack, safe. Allocating a list-based stack on the heap handles arbitrary nesting depth safely without call stack limit risks. The interviewer will then ask, how would you write a memory-efficient flattener that processes elements lazily as a stream? Implement a Python generator using recursion with yield/yield-from, or an iterative generator maintaining a stack, yielding elements one by one to support streaming contexts. The interviewer will then ask, if strings must be split into lists, but other scalars must be preserved, how does type logic change? Adjust the type checks. Explicitly verify if an item is a list or tuple, and not a string or dict, to decide whether to unpack or yield.